Good morning all of you. In the last session I had completed the plate load test and CBR test. Okay. In today's session I will move on to the numericals on CBR test and plate load test. Okay. Okay. Numericals on CBR test. Okay. The first problem it is the load penetration values of CBR tests conducted on two soil specimens of a particular soil are given below. Determine the average CBR value of the soil if 100 division of the load dial represents 190 kg load in the calibration chart of the proving ring. Okay. See here, penetration of plunger in Nm and load dial readings in divisions, that is for specimen number 1 and specimen number 2. Okay. See here, for 0 it is 0 and 0. For the 0.5 mm it is 8 and 0.5, and for 1 mm it is 15 and 1.5, and for 2 mm it is 29 and 13, and for 2.5 mm it is 34, 20, like that. Is it clear? Okay. And what you are going to do is, first you have to draw the graph. Okay. In the x-axis there is a penetration of the plunger in mm, and in the y-axis it is a load dial readings. The y-axis load dial readings in terms of divisions. Okay. First take a scale about 1 centimeter is equal to 2 mm in the x-axis, and in the y-axis 1 centimeter is equal to 10 divisions. Okay. As you seen from the graph, okay, here you have an x-axis, that is a penetration of the plunger in mm, 1 centimeter is equal to 2 mm, and you may see that y-axis it is load dial readings in divisions, 1 centimeter is equal to 10 divisions. Okay. And here we have a penetration values from 0 to 12.5. Okay, and corresponding load dial readings we have for specimen number 1 and specimen number 2, and you may see that there are two graphs. Okay, one curve is for specimen number 1, another curve is for specimen number 2. Is it clear? Okay, and from that figure, okay, whatever the graph you are seeing now, that is the graph corresponding to the given values. That is the graph corresponding to the given values. Okay. For specimen number 1, okay, you may observe here in the graph for the specimen number 1, the curve is convex throughout. The curve is convex throughout. Therefore, there is no need of correction. Okay. See here, and for the specimen number 1, from graph, okay, load dial readings, okay, at 2.5 mm penetration, is equal to, okay, see here, for the first curve, that is specimen number 1, for 2.5 mm penetration, what is the load? Okay, it is about 33 divisions. It is about 33 divisions. What you are going to do is, in the x-axis for the 2.5 mm penetrations, draw a vertical line parallel to y-axis, okay, which touches the specimen number 1 curve. Okay, from that point draw a horizontal line parallel to x-axis, okay, that intersect your y-axis at certain point, that is the load dial readings corresponding to 2.5 mm penetration. From the graph for the first specimen, that is specimen number 1, for 2.5 mm penetration, the load dial readings will be 33 divisions. Okay, and in the problem they only given, okay, the load dial represents 190 kg for 100 divisions. Then for 33 divisions, how many kg? It is very simple calculation. Okay, if 100 divisions represents 190 kg, then what about your 33 divisions? What about your 33 divisions? It's very simple calculation, no? Means load at 2.5 mm penetration is equal to 33 multiplied by 190 by 100. 33 divided by 33 multiplied by 190 divided by 100. Okay, this will gives about 62.7 kg. 62.7 kg. Okay, and we know that CBR is the ratio of actual load causing 2.5 mm penetration divided by standard load causing 2.5 mm penetration and multiplied by 100. Okay, therefore CBR at 2.5 mm penetration, CBR at 2.5 mm penetration is equal to actual load causing 2.5 mm penetration is how much? It is 62.7 divided by standard load causing 2.5 mm penetration how much? It is 1370 kg, no? 1370 kg and multiply by 100. Multiply by 100. This will give the CBR at 2.5 mm penetration. Okay, what is the CBR at 2.5 mm penetration? 62.7 divided by 1370 multiplied by 100. You may get about 4.58. You may get about 4.58. Usually for the CBR value, okay, we are going to round off to the value after the point to the 1 digit. Okay, after the point it should be round off to the 1 digit value. Okay, it is approximately about 4.6%. 4.6% is the CBR of the specimen number 1 at 2.5 mm penetration. At 2.5 mm penetration. Okay. Similarly, you need to calculate the CBR value for the specimen number 1 at 5 mm penetration. Is it clear? Okay. This is regarding the CBR value of specimen number 1 at 2.5 mm penetration. Is it clear? Okay. From graph, load dial readings at 5 mm penetration is equal to 48 divisions. Okay, you may see from the graph. For the specimen number 1 at 5 mm penetration, you may get about 48 divisions. Okay. Then load at 5 mm penetration, is equal to 48 multiplied by 190 divided by 100. Okay, 48 multiplied by 190 divided by 100. This will gives about 91.2 kg. 91.2 kg. Next, therefore, CBR at 5 mm penetration, is equal to what? Actual load causing 5 mm penetration divided by standard load causing 5 mm penetration multiplied by 100. What is the actual load? It is 91.2, and what is the standard load? It is 2055 for 5 mm penetration multiplied by 100. Okay, you may get 4.4%. You may get 4.4%. Okay, and whatever the CBR value at 2.5 penetration, it is 4.6 percentage, and at 5 percentage, at 5 mm it is 4.4 percentage. Okay, then the CBR at 2.5 mm penetration is more than at 5 mm penetration, then that is adopted as the CBR value of the specimen number 1. Okay, in actual practice, the CBR at 2.5 mm penetration is more than the 5 mm penetration. Okay, if the 5 mm penetration CBR is more than 2.5 mm penetration, then the experiment is repeated for checking. But in this case, the CBR value at 2.5 mm penetration is 4.6 percentage, and the CBR value at 5 mm penetration is 4.4%, means usually the 2.5 mm penetration about 4.6% is more than 5 mm penetration of 4.4%. No, therefore the CBR value of the specimen number 1, it is 4.6%. Okay, hence CBR value of the specimen number 1 is equal to 4.6%. CBR value of the specimen number 1 is 4.6%. Okay, this is regarding the CBR test for the specimen number 1. Okay, next you may observe the graph. Okay, for the specimen number 2, we have a initial concavity. Okay, therefore the specimen 2 curve needs correction. Okay, what you are going to do is, for the specimen number 2, okay, we are going to draw a tangent from steepest portion of the curve. From the steepest portion of the curve, we are going to draw the tangent in such a way that the tangent should touches the x-axis at a point. Okay, then whatever the point that touches the x-axis, while drawing the tangent for the steepest portion, that will be treated as a corrected origin for that specimen. And you need to measure the 2.5 mm penetration and 5 mm penetration from that corrected origin, not from the 0. Okay, from the corrected origin we have to measure the 2.5 mm penetration and 5 mm penetration. For specimen number 2, after applying the correction, okay, you should get the low dial readings corresponding to 2.5 mm penetration and 5 mm penetration and calculate the CBR. Okay, after applying the correction, okay, from the graph, low dial readings at 2.5 mm penetration is equal to 31 divisions. Okay, load at 2.5 mm penetration, so 31 multiplied by 190 divided by 100. Okay, this will give us about 58.9 kg. Then therefore CBR value at 2.5 mm penetration is equal to what? Actual load causing 2.5 mm penetration divided by standard load causing 2.5 mm penetration. What is actual load? 58.9. Standard load is 1370 multiplied by 100. Okay, you may give us about 4.3%. 4.3% is the CBR value of the specimen number 2 at 2.5 mm penetration. At 2.5 mm penetration. Okay. Similarly, okay, measure the low dial readings corresponding to 5 mm penetration from the specimen number 2 curve. Okay. From the graph, the load dial readings at 5 mm penetration is equal to 46 divisions. Then load at 5 mm penetration is equal to 46 multiplied by 190 divided by 100. Okay, you may get about 87.4 kg. 87.4 kg. Then CBR value at 5 mm penetration, CBR value at 5 mm penetration is equal to 87.4 divided by 2055 multiplied by 100, you may get about 4.2%. You may get about 4.2%. So, you may observe here for specimen number 2, okay, the CBR value at 5 mm penetration it is 4.2%, and what about the CBR value at 2.5 penetration it is 4.3%. Means the CBR value at 2.5 mm penetration is higher than the 5 mm penetration. Therefore, the CBR value adapted as 4.3%. Okay. Therefore, CBR value of the specimen number 2 is equal to 4.3%. Okay, means for the specimen number 1, the CBR value it is 4.6%, and for the specimen number 2, the CBR value it is 4.3%. Then, okay, if you want the average CBR value of the sample, okay, then it is 4.6 plus 4.3 divided by 2. Average CBR value of the soil, is equal to 4.6 plus 4.3 divided by 2. Okay, you may get about 4.45%. Okay, usually we are going to round off to the one digit after the point. No, it becomes 4.5%. 4.5% is the average CBR value of the soil. Okay, 4.6% is the CBR value of the first sample, and 4.3% is the CBR value of the second sample. Okay, if you take the average, then you will give the average of the soil sample. Is it clear? Okay, this is regarding the CBR test numericals. Okay, is it clear? Okay, next we will move on to the numericals on plate load test. Okay, numericals on plate load test. Okay, the first problem, okay, the first problem on plate load test, it is a plate load test was conducted on a soakwood subgrade during monsoon season using a plate diameter of 30 centimeter. The load values corresponding to the mean settlement dial readings are given below. Determine the modulus of subgrade reaction for the standard plate. Okay, they have given the mean settlement values in mm and load values in terms of kg. For 0 it is 0, for 0.24 mm it is 460 kg, 0.52 it is 900, 0.76 is 1180, 1.23 it is 1480, and for 1.53 mm it is 1490, and for 1.76 mm it is 1640 kg. Okay, what we are going to do is, first we have to draw the graph. Okay, x-axis is the mean settlement values in mm and y-axis is the load values in terms of kg. Okay, x-axis is the mean settlement values in mm and y-axis is the load values in terms of kg. Okay. You may use the scale of x-axis 1 cm is equal to 0.2 mm and y-axis you may use the scale of 1 cm is equal to 200 kg. Is it clear? Okay, you may see from the graph. Okay, first you should draw the graph. In the x-axis mean settlement values in mm, in the y-axis load values in terms of kg. You may select the scale of 1 cm is equal to 0.2 mm in the x-axis and in the y-axis 1 cm is equal to 200 kg. Okay, so we have the values of x-axis, that is 0, 0.24, 0.52, 0.76, 1.02, 1.23, 1.53, 1.76. Corresponding load values we have. Using this you may draw the graph, okay, and you may get the curve like this. Okay, whatever the graph you may see here, no? Okay, this is the graph corresponding to the given values. Okay, after drawing the graph, what you are going to do is, for the 1.25 mm, what is the load? Okay, we can say that the load values corresponding to 1.25 mm, or we can say 1.25 mm in terms of centimeter, it is 0.125 centimeter. Okay, what we are going to do is, from the x-axis at 1.25 mm, you need to draw a vertical line parallel to y-axis, okay, in such a way that the vertical line should touches the curve at some point. Okay, from that point you draw the horizontal line, okay, parallel to x-axis which touches the y-axis at a point, that is the load corresponding to 1.25 mm or the load corresponding to 0.125 centimeter. Is it clear? Okay, as you seen from this graph, the load corresponding to 1.25 mm, it is 1490 kg. The load corresponding to 1.25 mm, it is 1490 kg. Is it clear? This is a very simple solution. Okay, go for the solution. Okay, from the graph, okay, the load value say L1 corresponding to 1.25 mm or we can say 0.125 centimeter is equal to 1490 kg. 1490 kg is the load corresponding to 0.125 centimeter. Okay, then mean bearing pressure P1 is equal to, mean bearing pressure P1 is equal to L1 divided by pi d1 square by 4. Okay, L1 it is 1490 kg, pi d1 is what? Diameter of the smaller plate they are given, it is 30 centimeter. Okay, 30 square divided by 4. You know that load by area will give the pressure, no? Okay, here the d1 is the diameter of the smaller plate, it is about 30 centimeter. Okay, 1490 divided by pi into 30 square divided by 4, you may give the mean bearing pressure, okay, at 0.125 centimeter. Okay, how much you get it? It will gives about 2.11 kg per centimeter square. 2.11 kg per centimeter square. It is the mean bearing pressure. Okay. Next, okay, modulus of subgrade reaction K1 for 30 centimeter diameter plate, 50 centimeter diameter plate, K1 is equal to what? P1 by delta. Okay, delta is 0.125 centimeter. Now P1 is 2.11 divided by 0.125 divided by 0.125. You may get about 16.88 kg per centimeter cube. Kg per centimeter. How come it is kg per centimeter cube? Your pressure, mean bearing pressure in terms of kg per centimeter square, then your deflection delta, that is mean settlement, that is in terms of centimeter, no, then it becomes kg per centimeter cube. Okay, the modulus of subgrade reaction K1 for 30 centimeter diameter plate, it is K1 is equal to P1 by delta, that is 2.11 divided by 0.125, you may get about 16.88 kg per centimeter cube is the modulus of subgrade reaction for the smaller diameter plate of dia 30 centimeter. But what they are asking in your problem? They are asking determine the modulus of subgrade reaction for the standard plate. What is the dia of the standard plate? It is 75 centimeter. Okay. If for 30 centimeter dia plate you have the modulus of subgrade reaction 16.88 kg per centimeter cube, then what about for 75 centimeter dia plate? You need to apply the correction, no? Okay, by applying the correction, you need to find the modulus of subgrade reaction for the standard plate K. Basically, it's very simple correction. Okay, modulus of subgrade reaction for the standard plate K is equal to what? K1 D1 divided by D. That is equal to K1 is 16.88, D1 is 30 and D is the diameter of the standard plate. It is about 75. Okay, this will give about 6.75 kg per centimeter cube. 6.75 kg per centimeter cube is the modulus of subgrade reaction for the standard plate. 6.75 kg per centimeter cube is the modulus of subgrade reaction for the standard plate. Okay, all of you understood, no? Okay, this is regarding the numericals on plate load test. Okay.